Here what we will cover today: an introduction to embedded system, the project's objective and the development tools. Next we will see PIC16F877M microcontroller. Next we will see components used in the project and block diagram of PIC16F877M microcontroller and working of the project. Next we will conclude it. So let's begin with basics of embedded system. What is an embedded system? An embedded system is a specialized computer system that combines both hardware and software to perform specific tasks. Think of it as the brain behind devices like washing machine, where dedicated software controls hardware components. These systems are designed for efficiency and reliability, often operating in real-time environment. There are several types of embedded systems. So we can see here standalone embedded system. In standalone embedded system, there are two types: slave standalone embedded system and independent standalone embedded system. In slave standalone embedded system, it is going to blindly follow the instruction given by the user. In independent standalone embedded system, it has an intelligent part that will think of its own to perform a specific task without human interference. And next we see real-time embedded system. In real-time embedded system, we have hard real-time embedded system, soft real-time embedded system, and firm real-time embedded system. And some other types of embedded systems include network embedded system. Like home automation projects, we connect all multiple devices together. So these are the network embedded system. And mobile embedded system, like our phone, smart mobiles, these are the mobile embedded system. And hybrid embedded system, those are the combination of two types of embedded systems. Like robotics and IoT, we use different types of embedded systems and combine it. This is hybrid embedded system. Next we will see the objective of the project. The goal of the project was to simulate a washing machine operation using PixemLab, mimicking real-world functionality in a digital environment. I analyzed key components like motor, keypad, and display, and programmed operational cycles based on parameters such as fabric type, water level, and load size. By simulating this process, I could test and refine the system's behavior without needing physical hardware, ensuring accurate control and user interaction. So you can see here the washing machine we have simulated using PIC16F877 microcontroller and PixemLab as a simulator. So we can replicate the process of washing machine in PixemLab. Next we go to development tools. What we have used: MPLAB XID environment, that is MPLAB integrated development environment, developed by Microchip. Next is Xe8 compiler, C compiler for 8-bit PIC microcontroller that converts the C code to machine code. Next we have PixemLab, a simulation tool for PIC microcontroller that simulates the real-time environment similar to the washing machine. Next we come to PIC16F877 microcontroller. We will see its specifications like type. It is a 8-bit microcontroller designed by Microchip technology, and it have Harvard architecture. We see the memory here: 368 bytes of RAM, 14 KB of flash memory, and 256 bytes of EEPROM. And the clock speed of the PIC microcontroller is up to 20 MHz. Input output pins, there are 33 input output pins, general purpose input output pins. Next we see the peripherals it have. It have two 8-bit timers like timer 0 and timer 2, and 16-bit timer, that is timer 1. And we also have communication protocols like USART, universal synchronous asynchronous receiver and transmitter. And we have serial peripheral interface, that is SPI. And we have inter integrated circuit, I2C. And one ADC, that is analog to digital converter, that contains of 10 bits, plus we have interrupt that is 14 interrupt sources, and we have voltages between 2 to 5.5 volt, and packaging is 40 pin dual inline package. Next we are going to see the components we have used in this project, like tactical switch and digital keypad, CLCD, timer, interrupt, buzzer, and fan. Let's first dive into tactical switch and we will see it. Here is the tactical switch. In microcontroller systems, tactical switches serves as an input control, allowing user to interact with devices. Pressing switch activates it on, while releasing it deactivates it, like off. A collection of such switches make up the digital keypad. In this project, we have used RB0 to detect the door status of washing machine, that is switch 1, and RB3 functions as switch 4 for scrolling or navigating through options, and RB4 acts as switch 5 to power on the washing machine and resume the operation, and RB5 is switch 6 used to stop or pause the current process. So let's see, next one is CLCD, that is character liquid crystal display, that is used to display ASCII characters and special characters. In this, it contains 16 interfacing lines. So this is the CLCD we are using. The key features of CLCD: it contains data lines, control lines, character displayed, and contrast adjustment. So you can see here the schematic of CLCD. They have given 16 cross 2, which is 16 characters, 2 rows. So here data lines are from D0 to D7, that is RD0 to RD7. D0 to D7 are 8-bit data lines that is used to send character data to LCD, that can operate in 8-bit mode or 4-bit mode. So we can choose to 8-bit or 4-bit. 8-bit is little bit faster than 4-bit mode. And control lines we have RS, RW, and E. That is, RS is register select, selects between command register and data register, that tells the CLCD that if the, let us think of RS equals to 0 or RS equals to 1, this tells the CLCD that we are inputting data or instructions. The CLCD can decide it is data or instruction. So we use this RS pin. And next we have RW, that is read or write, determines whether the data is to read or written, and enable pin to activate the read or write operation. Next we have character display. Here displays ASCII characters from A to Z, 0 to 9, any characters. It can display special characters also, like symbols, punctuation marks, and custom characters. Next we have contrast adjustment. Typically includes a contrast pin to adjust the visibility character of the screen. Like here we have V0, that is connected to POT, that is potentiometer, which we can control the brightness of the CLCD. Next we have digital keypad. Keypads are used by the user to provide binary input to a microcontroller system. Each key is typically a push button switch that sends either a logic high or logic low. This is a digital keypad that contains all the tactical switches. We can think of like an array of tactical switches. So it has two types of triggerings. The first one is level triggered. Here the input is activated when the constant voltage level, usually high, is maintained. So we can say this is level triggered. Example, a pin reads high as long as the button is pressed. The next one is edge triggered. Here activation occurs during a sudden change in voltage, either from low to high or high to low. So it is like a pulse. From high to low we can, it is a falling edge, and from low to high it is rising edge. See, so this is edge triggered. Next we can see keypad circuit configuration. We have two types of circuits like sourcing circuit and syncing circuit. In sourcing circuit, we can say the logic 1 is on and logic 0 is off. So quite opposite of that is syncing circuit. So logic 1 is off and logic 0 is on. Next we can go to timers. A timer is an essential binary counter that counts clock pulses from internal or external sources. It increments with each pulse and reset to 0 when it overflows. Optionally, triggering an interrupt if enabled. Timers are widely used for time delays, event counting, and pulse width modulation. As I have said, in PIC 16F877 microcontroller, the timer 0 is 8-bit. You can see here 8-bit timer is timer 0 and timer 2 also 8-bit. Timer 1 is a 16-bit timer. Next is an interrupt. A interrupt is nothing but a service request to microcontroller or microprocessor. An interrupt is a signal that prompts the microcontroller or processor to pause its current execution. It is generated by internal like timers or ADC or external button sensors or sources. The processor acknowledges the interrupt and temporarily halts ongoing tasks. It then jumps to an interrupt service routine, a special function that handles the events. After completing the ISR, the processor resumes from the exact point it was interrupted. So the process will going on. An interrupt occurred. So the interrupt will stop the current execution. The processor will acknowledge it and then it will jump to the interrupt and process the interrupt through an ISR, that is interrupt service routine. After completing it, it will resume the current process. So here are the interrupts, like we can see here hardware interrupt, software interrupt, and in hardware interrupt there are two types, maskable interrupt and non-maskable interrupt. Maskable means which we can ignore and non-maskable means which we cannot ignore. Like in maskable interrupt, we have two types like external interrupt and internal interrupt. Next we can see here buzzer. A buzzer serves as an audio indicator in washing machine system. It activates for 2 seconds when washing machine cycle is completed, signaling the end of the process. Additionally, it sounds a warning in door if the door is opened in the middle of ongoing washing machine program. So to alert the user of an interruption. So we can generally hear in the washing machine, like if you suddenly pull the door at the ongoing process, it will sound the buzzer. It also sounds at the last when the washing machine cycle is completed. So here in the project we have given RC1 pin as an buzzer. Next we are going to see the fan. The fan is used to simulate the motor of a real washing machine. It starts spinning as soon as any washing mode is selected and keeps running until the cycle ends. If the door is opened, the fan stops automatically for safety. The fan resumes spinning once the door is closed again. Here in Pixum Lab, we are using RC2 pin as fan. Next, let us dive into the architecture of PIC16F877A microcontroller, the brain behind our washing machine simulation. This 8-bit microcontroller uses a Harvard architecture with a separate program and data buses for efficiency. Here, the flash memory holding 14 KB feeds the program counter and instruction register, while the 368 bytes of RAM and register handles real-time data. The central ALU, powered by the oscillator and timing circuits, process instructions, and supported by a power-up timer, watchdog timer, and brownout reset for reliability. Data flows through 8 level stack and multiplexer for GPIO ports from port A to port E, offering 33 pins for inputs like the keypad and outputs like buzzer and fan. Here we can see the key peripherals include 3 timers: timer 0, timer 1 and timer 2 for cyclic timing, a 10-bit ADC for a sensor data, and interfaces like USART, SPI and I2C for communication. The data EEPROM stores settings and interrupt from external sources like the door switches, ensure responsive control. This robust design made our simulation precise and functional, and I will show how it works in the next. Okay, let's start the demo. In the demo we are going to see two things. First one is how to create a project in MPLAB, and the second one is what header files and source files we have used to make a washing machine project. So let's see the first one, how to create a project in MPLAB. Let's go to file, click new project and click next. In family, select the family mid-range 8-bit MCU. In device, type pick 16F877A. So here is the microcontroller. Select this device, select no tool and click on next. Here select the X8 compiler and click on next. Write any project name like washing machine and click on finish. This is the way you create a project. Now I have already created a project washing machine here. So the second one is to see the source files and header files we have used to create a washing machine project. So let's see the source files. These are the peripherals we have used like clcd.c, digital keypad.c, timer.c. In the timer we have an interrupt like interrupt isr.c. So to have a function definitions in an organized way, we have created washing machine function.c, where you can write all the prototypes and function definitions here. Now let's compile the program. Here you can see the build option, and we have built successfully. Okay, now let us see the project in action. We have opened PiximLab. In PiximLab we can go to file, load the hex file which we have generated by building the program in MPLAB. So go to file, load hex file. Here we can see washing machine production.hex file. So open it. Now we can see the display here. Press key 5 to power on the washing machine. So here key 5 is RB4. So click on it. After pressing key 5, we can see the display powering on the washing machine. Here are the wash programs like daily, heavy and delegates. We can scroll or navigate through RB3, that is switch 4. So press switch 4. So to select the highlighted option, we can long press the switch 4. So I am selecting heavy and long press it. After long pressing, we can see the next screen, that is water level. We have options like auto, low, medium, high and max. So we can, as it is, we can scroll it through switch 4. So we can press switch 4 to scroll. So now I am going to select medium as an option. To select it, press again switch 4. So to select the highlighted option, Now long press the switch 4. Now we can see press switch 5 to start and switch 6 to stop. So press switch 5 to start. Now we can see here we have selected program heavy and the time is 50 seconds. Now we can see here the fan has turned on, which is a motor in a washing machine, and the timer has turned on. It starts counting. So to pause, we have given switch 6. So to pause the program, we have to press switch 6. So the program has paused now. So to resume it, we can use switch 5. So here is the switch 5. Now the program resumes. Here we are using RB0, which is switch 1 as a door. So if we press it, then the buzzer will be on and door is open. Please close the door. So when you release it, the fan will again turn on and the function will continue. So we can see here rinse is turned to spin. When the timer has completed, the buzzer will get on and we can see here the display program complete, remove the clothes. So it will return again to the starting position, which is washing program. It will show the programs like heavy, delicates, whites. So again you can perform the operation. Next we conclude that this project successfully simulated a washing machine using the PIC16F877A microcontroller in PICSIMLab. I applied embedded C programming, leveraged the microcontroller features and integrated components like the CLCD, keypad and buzzer to create a functional system. This experience deepened my understanding of embedded system and prepared me for future challenges in this field. At last, what we have learned? We have learned detailed C and embedded C programming languages, and we have gained in-depth knowledge of PIC16F877A microcontroller architecture and its functionalities. Next, we have acquired hands-on experience with PICSIMLab for simulation and testing. Next, I thank you all for listening and for your kind attention throughout this presentation. I am deeply grateful to Emertxe for providing me with this invaluable internship opportunity, which has been a cornerstone for my learning journey. I also extend my heartfelt thanks to all the teachers for their support and insightful explanation. Thank you once again.